Hi, my name is Tanvika Dasari, and welcome to our skills video. We are RoboSub, Harvey Mudd College's RoboSub team, and we will be presenting our current SLAM design under the sensor optimization category. Our presenters for this video are on the left section. Namely, I will be going over the subsystem overview of the SLAM algorithm, Hal Wong will be going over the competition strategy, and Chris Herrera will be covering development and testing. So on the left are team members currently involved in the design and implementation of SLAM, while the members to the right, Seth Isaacson, Daniel Yang, Arya Gautam, and Shivam Malpani have significantly contributed to our design by prototyping FastSLAM 1. So SLAM stands for simultaneous localization and mapping, and is used to determine where the robot is relative to its unknown surroundings. So both our current pose and the map outputted by SLAM is used by later subsystems to directly move the robot and accomplish tasks. So to create a map of the pool, SLAM uses information from multiple sensors, like data from the inertial measurement unit and cameras, to fuse information such as the robot's velocity and its distance to its surroundings. By using information from multiple sensors, we are able to gain a more confident understanding of our robot pose and our path, rather than just using one piece of data, like odometry, shown in the figure. SLAM also allows us to gain more information on the robot's surroundings and map obstacles such as buoys, gates, and targets, allowing us to implement better competition strategies. In the competition, we hope to dry run to create a base map, which will be later used for later runs. This allows us to further remove heuristics and human priors in robot planning and better rely on robot autonomy. However, as SLAM depends solely on measurement data in our control model, algorithms that are resistant to sensor and movement noise are required. We decided to implement the algorithm FastSLAM 2.0.
Now we'll discuss our competition strategy. In deciding which SLAM algorithm to use, we focus on 4 principles: reliability, extensibility, performance, and learning opportunities. Given that our primary perception system is a camera, the more popular SLAM algorithm to adopt would be visual SLAM. However, based on the team's experience, the overexposure of the afternoon light and the water quality degradation after a few days during the competition often render many images unusable. For example, the 2 images on the site are images of the gate before and after computer vision processing. The gate is only visible after extensive heuristic processing, and this approach is not always reliable. Of course, there are remedies to these challenges, but one of the team's design principles is reliability. We do not want to place too many dependency on a single system. As such, we think building our entire sensor and navigation system on an only occasionally reliable visual system is not wise. On the other hand, one of the highest performing non-visual SLAM, called FastSLAM, depends only on the range and bearing information of the obstacles. Since it does not depend on the particular sensor that produces these information, it provides the team with an option to diversify the team's perception dependency and to increase the team's overall system reliability. Another principle that favors FastSLAM is extensibility. Although we currently only have a single camera, we want to be able to easily incorporate more cameras and different sensors in the future, such as sonar and hydrophone. Therefore, adopting a visual SLAM might restrict our ability to incorporate these sensors in the future. Guided by this forward design thinking, we find the FastSLAM option even more appealing. We will now explain what FastSLAM is. FastSLAM approaches the SLAM problem with a key insight. Given the true robot path, estimating the position of each landmark can be done independently. This means that if there are n landmarks, FastSLAM can be simplified into the problem of estimating n+1 objects, which are the robot pose and n landmark pose. To estimate the robot pose, FastSLAM uses a particle filter, since a particle filter can capture non-parametric distribution of solutions and maintain multiple hypotheses, which is useful in a challenging course. To estimate each of the n landmark pose, FastSLAM uses an independent low-dimension EKF for each landmark, in which the low dimensionality ensures computational efficiency. To summarize, FastSLAM algorithm is a particle filter where each particle consists of an independent EKF for each landmark. Specifically, our system uses FastSLAM 2 algorithm. FastSLAM 2 improves over FastSLAM 1 by using sensor measurements when estimating the new pose of the particles. This improves the accuracy of particles. So more particles in proportional distribution receive higher weight, and less are eliminated. This results in better particle diversity, since less elimination means that it is less likely for all particles to share the same parent particle. This means that the algorithm is less likely to eliminate different paths and different hypotheses. In turn, this allows FastLAM2 to converge more quickly and with fewer particles, especially when motion model is noisy compared to the sensor measurements. While we do not expect we have small measurement errors, we want to maintain particle diversity in order to keep track of multiple hypotheses because of the difficulty of the course. Besides FastLAM2's higher performance, we select this algorithm because there is no available implementation that we can find, and this can be a great learning opportunity. Overall, we are 70% confident that our algorithm will work in the real competition because it performs relatively well during simulation, and we are more and more familiar with the algorithm. The only concern we have is the lack of real-life testing.
I will now be discussing the development and testing of our algorithm. Because of the complexity of the algorithm, FastLAM2 is very difficult to debug. It includes many components, and it can be difficult to identify which of them is responsible for the system not performing as expected. In order to verify our implementation, we reviewed multiple papers by the authors, as well as the famous robotics textbook, Probabilistic Robotics. Our verification was made more difficult by the fact that there are not any existing implementations that we can find, so we were driven to learn and debug through experimentation. One method that was very useful was hard coding in certain parts of the data to evaluate the algorithm's performance in another part. For example, in order to test just the localization, we hard coded the ground truth positions of the landmarks into every particle. Similarly, in order to test just the mapping, we hard coded in the ground truth path into every particle. As we verified more of the algorithm, we were able to hard code less, such as just the ground truth compass measurements. We are still continuing this process, but the algorithm currently operates well without any ground truth landmark locations, or any of its ground truth path. Since the pandemic has limited our ability to work with the robot, our primary method of testing our implementation has been through existing datasets. We used the Multi-Robot Cooperative Localization and Mapping, or Mr. CLAM dataset, published online by the University of Toronto Institute for Aerospace Studies, UTOs, which can be seen in the top image. It consists of sets of bearing and range measurements, as well as velocity commands for the robot. The advantage of using this dataset is that it is easily available and simple to work with. And it is also ideal for testing our implementation of FastLAM, since the kind of measurements it has are the type FastLAM is meant for, and the type of measurements that we'll be using in competition. One major drawback, though, is that the Mr. CLAM dataset is for robots navigating in a 2D space. We don't expect this to be a huge problem because we have decided that it makes sense to separate the SLAM problem into a 2D component in the horizontal plane and a 1D depth component, since we have reliable depth data. Another drawback is that since the dataset is pre-recorded, we cannot test the interaction between the data and using SLAM to decide where to go. So results may not be completely transferable. The bottom animation shows the results of testing our algorithm on the dataset, where the red line is the path estimated by SLAM, and the blue line is the ground truth path. Testing with the dataset consists of running our algorithm on the data collected by a single robot in the dataset and computing the mean squared error between the path output by the algorithm and the ground truth path in the dataset. Recognizing the limitations with the pre-recorded data in the dataset we tested with, we decided to create a custom simulator to have more control over the robot and the data the algorithm is being tested on. Our custom simulator generates the same type of data as the dataset, i.e. range and bearing measurements and velocity commands. One advantage is that we have control over how noisy it is, and another is that the results of the FastLAM algorithm can also influence the data generated, which is more realistic and is not possible in the pre-recorded dataset. As a concrete example, if the robot is uncertain about the location of a landmark in our simulation, it would be possible for it to move around the landmark to make more measurements of it. The major drawback of a simulator such as this are that it uses idealized models to generate the data and cannot capture all the nuances of the physical systems like the dataset can. An example simulation is displayed on the right, where red is the estimated path that FastLAM calculates and blue is the actual path that the robot takes using the map FastLAM generates. In this simulation, we initialize landmark poses noisily, and the robot is tasked to move towards the landmark until it hits a close enough zone, before moving on. As we can see in the animation, the trajectory SLAM generates closely matches the real trajectory. Moreover, as shown on the top right corner, the landmark poses are corrected as the robot moves towards that region. This gives us confidence that our algorithm is performing well and will be extensible to competition. In order to address the drawbacks of both the dataset and our custom simulator, we eventually plan to use a more realistic simulator. Eventually, we also hope to be able to test our algorithm in the pool. Our next step after that will be to begin integrating our algorithm with the navigation and mission subsystems, which use the output of SLAM to make decisions about how the robot should move. Finally, we hope to be able to take advantage of RoboSub's specific features, such as the shape of the pool, or access to reliable depth measurements to improve our algorithm. And these are our references. Thank you for listening. This SLAM project has been a great opportunity to learn more about different robotics topics, including EKFs, particle filters, and localization, etc. I hope you enjoyed our presentation.